Hello! I'm Professor Von Schmohawk, and welcome to YU. In the last several lectures, we saw how identifying a rational function's vertical asymptotes is an important step in sketching the function's graph. In this lecture, we will see how to identify several other types of asymptotes that can also be helpful in understanding a rational function's behavior. In the previous lecture, we saw that vertical asymptotes occur at x values that cause the value of the function's denominator to be 0. For example, this function's denominator has a value of 0 when x is negative 2. As a rational function's graph approaches a vertical asymptote, the value of the function's denominator approaches 0, causing the function's value to grow without bounds in the positive or negative direction. But even though a function's graph can approach infinitely close to a vertical asymptote, it can never intersect that asymptote, since when the denominator's value is 0, the function's value is undefined. A vertical asymptote is therefore a vertical line that a function's graph can approach arbitrarily close to, but can never intersect. Although a rational function may have any number of vertical asymptotes or no vertical asymptotes, rational functions will always have exactly one non-vertical asymptote. For instance, in addition to its vertical asymptote, this function also has a horizontal asymptote that lies on the x-axis. Unlike vertical asymptotes, a function's graph may intersect or cross its non-vertical asymptote. For example, this rational function crosses its horizontal asymptote. However, as x values continue to grow, eventually a rational function's graph will approach its non-vertical asymptote without intersecting the asymptote. Although the term asymptote typically refers to linear asymptotes that are either vertical, horizontal, or oblique, asymptotes can also be curves called curvilinear asymptotes. So, unlike vertical asymptotes, which occur at x values where the function's denominator approaches 0, causing the function's value to grow infinitely large, non-vertical asymptotes occur when as x takes on increasingly large positive or negative values, the graph's distance to the asymptote becomes increasingly small. As x takes on large positive or negative values, a rational function's graph will always approach the graph of a polynomial function that describes a non-vertical asymptote. In this example, the graph approaches an asymptote described by the polynomial function f of x equals 1/2 x. The simplest non-vertical asymptotes are horizontal lines. For example, this rational function has a horizontal asymptote described by the constant polynomial function f of x equals 3. And this rational function has a horizontal asymptote described by the constant polynomial function f of x equals 0. Curvilinear asymptotes are described by higher degree polynomials. For example, this rational function has a curvilinear asymptote described by the second-degree polynomial function 1/4 x squared. And this rational function has a curvilinear asymptote described by the third-degree polynomial function 1/7 x cubed. We can determine which type of non-vertical asymptote a rational function has from its numerator and denominator's leading terms. So let's see how this works. When we introduced rational functions, we showed that a rational function is a ratio of polynomials, and when written in standard form, the terms of these polynomials are arranged so that their exponents decrease going from left to right. Since the leading term of a polynomial in standard form has the largest exponent, as x takes on large positive or negative values, the leading terms of the numerator and denominator grow much faster than the other terms, and therefore determine the general shape of the curve that the function's graph approaches for large x values. The type of non-vertical asymptote can be determined by comparing the exponents of the numerator and denominator. And if the rational function is in standard form, these will be the exponents of the numerator and denominator's leading terms. To show how this works, let's call the coefficients of the leading terms a and b, and the leading terms exponents n and m. If the value of the numerator's largest exponent n is less than the denominator's largest exponent m, the function will have a horizontal asymptote located on the x-axis. And if the value of the numerator exponent is the same as the denominator exponent, the horizontal asymptote will be located a distance from the x-axis determined by the ratio of coefficients a and b. On the other hand, when the numerator exponent is greater than the denominator exponent, the function will have either an oblique asymptote or a curvilinear asymptote. So whenever we see a rational function whose largest numerator exponent is less than or equal to the largest denominator exponent, we know that that function will have a horizontal asymptote. If the largest numerator exponent is less than the largest denominator exponent, that asymptote will lie on the x-axis, and if the largest numerator exponent is the same as the largest denominator exponent, that asymptote will lie above or below the x-axis. So let's determine the horizontal asymptotes for a few rational functions. Given any rational function, to determine its non-vertical asymptote, we start by selecting the leading terms of its numerator and denominator. Since in this example, 18x squared is the only term in the numerator, 18x squared by default is the leading term. The denominator, on the other hand, has two terms, so the term with the largest exponent is the leading term, and when calculating this function's asymptote, all other denominator terms can be ignored. We can then determine the type of non-vertical asymptote that may exist by comparing the numerator and denominator exponents. Since in this example, the value of the numerator exponent is less than the denominator exponent, the function will have a horizontal asymptote located on the x-axis. And this function has a graph that looks like this. Another example of a rational function with a horizontal asymptote located on the x-axis is the function 1 over x. Since this function's numerator and denominator each consist of a single term, both of these terms are by default leading terms. We also know that the denominator x has an implied exponent of 1, and the numerator 1 is equivalent to x with an exponent of 0. Therefore, since once again the numerator exponent is less than the denominator exponent, this function has a horizontal asymptote located on the x-axis. And so the function 1 over x has a graph that looks like this. As one last example, let's look at the rational function 0.8x squared plus 0.2x plus 0.05 over 0.01x to the 7th power minus 0.3x squared plus 1. Although this rational function appears to be complicated, we can determine its non-vertical asymptote simply by examining the leading terms of its numerator and denominator. And since the numerator exponent is less than the denominator exponent, we know that this function has a horizontal asymptote located on the x-axis. And the function's graph looks like this. In each of these examples, since the exponent of the numerator's leading term was less than the exponent of the denominator's leading term, these functions all had horizontal asymptotes located on the x-axis. This happens because when the largest exponent of the numerator is less than the largest exponent of the denominator, as the value of x grows, the numerator's value grows much more slowly than the denominator's value. And so, for large values of x, the rational function's value approaches 0. However, as we mentioned earlier, if the exponents of the numerator and denominator's leading terms are the same, the rational function will have a horizontal asymptote that is not located on the x-axis. The distance of the horizontal asymptote above or below the x-axis is determined by the ratio of the leading term's coefficients a and b. If the value of a over b is positive, the asymptote will be located above the x-axis. And if the value of a over b is negative, the asymptote will be located below the x-axis. So let's look at a couple of examples of rational functions with horizontal asymptotes that are located above or below the x-axis. One example of a rational function with a horizontal asymptote that is not located on the x-axis is the function 8x cubed minus 3 over 4x cubed minus 3x plus 2. Once again, we start by selecting the leading terms of the numerator and denominator. Since in this example, the exponents of the numerator and denominator have the same value, we know that this function has a horizontal asymptote located a distance above or below the x-axis determined by the value of the numerator coefficient divided by the denominator coefficient, which in this example is positive 2. This function therefore has a horizontal asymptote located 2 units above the x-axis. So the function's graph looks like this. As one last example, let's consider the function 2x cubed minus 4x squared plus 1 over negative x squared times the quantity x minus 2. We once again start by selecting the leading terms of the numerator and denominator. However, although the numerator in this example is written as a polynomial in standard form, the denominator is not. We must therefore first put the denominator in standard form by multiplying negative x squared by the expression in parentheses. Multiplying negative x squared times the terms in parentheses we get negative x squared times x, or negative x cubed, and x squared times 2, or 2x squared. We can now select the numerator and denominator's leading terms. Since their exponents have the same value, this function has a horizontal asymptote located a distance above or below the x-axis determined by the numerator coefficient divided by the denominator coefficient. Since the denominator has an implied coefficient of -1, the numerator coefficient divided by the denominator coefficient is -2. Since this value is negative, this function has a horizontal asymptote located 2 units below the x-axis. And the function's graph looks like this. In each of these examples, since the exponent of the numerator's leading term was the same as the exponent of the denominator's leading term, these functions all had horizontal asymptotes that were not located on the x-axis. To understand why this happens, let's take a closer look at one example. In this example, the leading terms of the numerator and denominator are both x cubed. Since these exponents are larger than the exponent of any other term in the numerator or denominator, as x takes on large values, these terms grow much faster than the other terms, and the values of the numerator and denominator each approach the values of their leading terms 8x cubed and 4x cubed. So for large x values, the function's value approaches the ratio of these two leading terms. However, this ratio can be simplified. Since x cubed in the numerator and denominator will always have the same value, the x cubed factors cancel. And so for large x values, the function's value approaches 8/4 or +2. Therefore, this function has a horizontal asymptote 2 units above the x-axis. So far, all the examples of non-vertical asymptotes that we have seen have been horizontal. But non-vertical asymptotes can also be slanted lines called oblique asymptotes, or curved lines called curvilinear asymptotes. In the next lecture, we will see how to determine if a rational function has an oblique or curvilinear asymptote and how to calculate that asymptote's shape and position.